Let's start. So welcome everyone. It's my pleasure to introduce today's speaker, Dr. George Pavlidis, Tenure-Track Assistant Professor of Mechanical Engineering at the University of Connecticut, Yukon, USA. He earned his Master of Engineering in Mechanical Engineering from Imperial College London in 2013, and his Ph.D. degree in Mechanical Engineering from the Georgia Institute of Technology in 2018. He also was awarded the National Science Foundation EAPSI Fellowship to investigate the thermal conductivity of gallium nitride in Japan under the supervision of 2014 Nobel Prize winner Hiroshi Amano. Prior to joining the department, Dr. Pavlidis was a National Research Council postdoctoral fellow at the National Institute of Standards and Technology, NIST, Gaithersburg. His research is primarily focused on assessing the reliability of new generation wide bandgap transistors using optical and electrical techniques with high spatial and temporal resolution. We are excited to hear about thermal metrology for emerging semiconductor devices, which is the topic of Dr. Pavlidis' speech today. I now invite George to take the floor. It's all yours.
All right. Thank you so much for that very kind introduction, and thank you very much for inviting me to give this talk today. Okay, so as the title says, I'm going to be talking today about thermal metrology techniques, and specifically for semiconductor devices. Just to follow up on that intro, I know there's an intro about me, but I wanted to introduce my lab because those are the people that are really doing the work. So here at UConn, we're part of this Connecticut Power Electronics Center of Excellence, as well as this Clean Energy Institute. And we focus on what I'm going to show today is about thermal imaging for these types of semiconductor devices, as well as thermal management. And these are the three students that are the main drivers of all the work in my lab right now. They're all three PhD students. So on top of that, just to give you a broader overview of my work, on top of the thermal imaging and the thermal management, we also look at other processes and other types of devices, not just transistors. Devices for memory and for neuromorphic computing, where you have to start measuring. It also concerns thermal metrology, but going from a microscale to the nanoscale. If you are interested in that, I'm happy to talk to you on the side and talk to you about thermal property mapping also on the nanoscale. Okay, so an outline of the talk here, what I'm going to go through over the next 40 minutes, hopefully, is why bandgap semiconductors? Why are they relevant and interesting? Why is there a thermal problem with them? And what are the challenges that we're trying to overcome? And then I'm going to do a deep dive into one of the techniques, the thermal reflectance imaging, and give you a case study about two different technologies, one with gallium nitride and then one with aluminum gallium oxide. So just to set the background and the motivation for gallium nitride, that first technology I'm talking about, this all has to go back to the material properties of these semiconductors. So probably what you're all familiar with is silicon technology, right? There's Silicon Valley. There's a lot of electronics being made with silicon, and that's never going to go away because it's such an established technology and everything's very cheap there too. But these new semiconductors that people have discovered how to make with high quality, and that's why the Nobel Prize, the professor I worked with at Japan was awarded, was this material that you can go to higher bandgap, and that allows you to withstand higher voltages. You can actually operate your devices at a higher temperature. Your mobility is higher when you are operating at an elevated temperature. And then also for some of these cases, you can get a higher switching frequency. So what does that translate to? That really translates to the fact that you can make power electronics that are very efficient. You can also make RF devices, radio frequency devices, that transmit signals very efficiently as well. And the whole purpose of this is that you can do these at higher performance, but at smaller dimension. So these are kind of the three areas. Like I said, the power electronics, now you can reduce your laptop charger, right? A lot of people are buying these chargers that are just look like a phone charger for your laptop now. Those actually have gallium nitride technology already in them, as well as all the 5G advertisement for phones and how fast you can have internet on your phone. Those base stations are using those types of technologies. The primary factor that actually gallium nitride was used for before getting into this area is for LEDs. And I think now almost like 85%, 90% of LEDs are made from gallium nitride as well. Okay, so you can fabricate all these devices on a wafer. And also, the other thing to think about here about the operation of these devices is not just one mode of operation. You're not just looking at a steady state thermal problem, you're looking at a transient problem in a lot of cases, and it's at different frequencies. It can range from the gigahertz range all the way down to the kilohertz range. So if we take an example, this is probably like the state of the art now in commercial devices, this AlGaN high electromobility transistor. What's happening here in this device is you have a source gate and drain, and the way to think about this is that the gate can modulate your current in the device and turn it on and off. These electrons, you typically have a very high voltage on the drain here, on the order of like, it could be up to like 100 volts. And then you have this negative voltage on the gate that you can apply to close the channel. If you're looking at the potential, it kind of looks like this, right? Your source is 0, goes down a bit negative, and then there's a large voltage change when you go across this channel from the gate to the drain. This large change of potential translates to electrons gaining a lot of energy. So all this energy that they gain and they're accelerated, they want to dissipate. Now, the easiest process to convert all this energy from electrons is to transfer it to optical phonons. Now, as we know, this being the thermal transport talk, optical phonons aren't good at carrying heat. We have to use acoustic phonons. So from the optical phonons, you have to transfer that energy to the acoustic phonons to remove that heat, primarily through conduction from this hotspot in this device. So that inefficiency is what causes this heating. And now you have to think about that this dimension is almost a micron or less, where you have this extremely localized hotspot. And now, if you look at this from a thermal perspective, you have this hotspot temperature that's at the interface of a metal and a semiconductor. These materials expand at different rates. This also is going to cause a large stress to develop between the two materials. That large stress can translate to many different types of failure modes. One thing that can happen is that these devices have defects that form from the stresses, and then those defects can expand, and then basically they can stop your device from working. You can have a current collapse in the device, and no electrons can go through. So we need to remove the heat, and either, I mean, convection, just natural convection. We want to avoid doing active cooling because these go into like our phones and other things. We're trying to keep the costs down. So we're trying to remove the heat as much as possible through down the substrate through conduction. Now, most of these electronics, I told you about gallium nitride, they don't have available wafers that are the same materials at the size that silicon wafers are made at. So the way to reduce the cost of this technology is to grow these really good semiconductor materials on top of a large scale wafer like silicon. Now you've just created a large thermal boundary resistance. So that interface is going to cause problems for you trying to get this heat out. And this is just an image here showing you what these interfaces look like. And this could be a whole other talk I could give to you about how to engineer this interface and what companies are doing to try to make this better, reduce the thicknesses, different recipes, and what to grow as a transition layer. So the main focus of this talk, however, is how can we design our devices to maximize their performance and reduce that junction temperature? So there are a few things that we have to consider when thinking about the device heating and how you can improve the thermal performance and maximize your power here. One thing is this joule heating that I explained to you. It's actually very dependent because it's based on the electrons and where they move right on the electrical field. In some cases, for the radio frequency devices, the electric field changes quite a bit through the operation. And that means that your profile also changes. So there's been a lot of work done on simulations to predict how this has changed. And now also measurements are starting to come into play. But really, most of the previous work that's been done is changing your gate bias conditions here and then seeing how your temperature profile changes with that gate bias condition for the same power densities here. So you can just see here on the right here that in this case, you can get an increase in about like 15, 20 degrees near the gate here just by going from positive 1 volts to minus 1 volts here. So this is important because if you're trying to do reliability testing and predict the lifetime of these devices, you want to put these also in rocket ships and they have to last a very long time. RF testing to bias a device in radio frequency operation is very expensive. So having accurate simulations and some experience to predict what's happening is very important for engineers to understand how to design these devices better. So apart from understanding the bias dependence on the Joule heating, another issue is when you look at the design parameters, the few things that you can alter in the device is the dimensions. So the dimensions of the gate, this finger width here, the more you elongate it, you're going to increase your thermal resistance. And then you have multiple gates, multiple channels. That distance between the channels is also going to affect thermal resistance, right? So there's some optimization there where you have to do to find out these best finger widths and end gate pitches as well. This graph here kind of shows the number of the gate fingers, how the thermal coupling and thermal crosstalk effects increases the thermal resistance. This is just in the inverse, it's showing power capacity. So it's the inverse of the thermal resistance here. So wider spacing allows you to get the more power. Okay, and apart from just the distribution, then you also have to think about the transients for allowing these devices to cool down and heating up. So do you reach the steady state temperatures, and when you cool down, are there any effects of heat accumulation as well? So all of these, what they're leading to, the motivation here is that you need some type of technique that you can estimate the temperature accurately, the peak temperature in this small area, less than a micron. And you also want a technique that can map the distribution because you need to understand thermal crosstalk effects between different channels as well. So there are many techniques that exist. And as I said, I'm going to focus on one. But just to give you a brief overview of the other techniques that the industry uses and what people use in academia, I'll just start off first with the most basic one for these types of devices, and that's infrared thermal imaging. So infrared is based on measuring the radiation from the device with an IR thermal camera, right? And this technique is nice to get an overall like view of the whole device, and you can kind of identify where it's getting hot, right? This picture shows you where it's failing, and you can kind of predict that. This is very quick. The only thing is if you're trying to actually evaluate the thermal resistance, it's a bit tricky here because IR wavelengths, right, they have a very low energy. These materials have a very high band gap. So they're mainly transparent to these materials. So the emission you're receiving when you have your camera up here is receiving emission from all these different layers. And that means you're going to be underestimating because that it's an average of all those signals. So it's good for identifying spatially where there's a problem, but probably to get an accurate thermal resistance is not the best technique here. Also, spatially, you are limited. These are long wavelengths. So if you're trying to map something that's less than a micron or 500 nanometers, it's going to be pretty difficult using IR. People then started doing, since these are being built by electrical engineers, is to look at electrical parameters that are temperature dependent. So you can calibrate, for example, the resistance of that gate metal that's close to the hotspot. And then you can look at how that resistance changes over time and also for different power conditions. Now that's a great technique, and it's a very good in situ monitoring technique. But you're also limited to what you're averaging across. So there's no spatial resolution really there. And then what's been used a lot, especially for these specific types of devices, has been Raman thermometry. So that's just Raman spectroscopy, where you're measuring the phonon frequencies of these different materials. So that lets you differentiate between this gallium nitride, or the substrate. And that change, the phonon frequency is dependent both on temperature and stress. And there's a way to decouple these effects by monitoring two different Raman frequencies at the same time for one material. So you can estimate both the temperature rise in the material for a given spot size, which you can get down to 1 micron, and then you can also estimate the thermal stress that's developed in the material. As you can imagine, though, This is a point measurement technique, so if you're trying to take a map, it takes quite a bit of time to map across the whole device. So looking at this, one of the alternative solutions here to try to achieve this imaging technique that you can get both the transient capability and the spatial resolution that you need would be thermoreflectance imaging here. So this technique is based on the principle that you're shining some type of single wavelength illumination onto the surface, and you measure the reflection of that surface. So the reflection, based on the material you're using, a lot of them, the reflection changes linearly with temperature. So if you could take advantage of that linear relationship, you could estimate the temperature based on the change in reflectance if you were able to extract the thermoreflectance coefficient of that surface. Now, maybe many of you have seen a lot of papers or work on time domain thermoreflectance, which is a technique where it's a pump probe technique where you're using the same principle, but you're just looking at the change in reflectance over like a certain time period, and then you're fitting that to some solution to extract the thermal conductivities of different thin films. This is based on the same principle, except this technique for the imaging part is we're just using the reflection intensity for each pixel in the CCD, and then we're mapping all those pixels out and then getting a temperature rise for each of the pixels. So this technique is great for metals. You have very high reflectance. It's pretty easy to get the thermoreflectance coefficient when you calibrate these materials. One thing to note, though, that your reflection changes depending on your wavelength. So it's something you need to take care about and account for when you're calibrating these types of measurements. Now, just to explain a bit more of the setup that we have in our lab and what we use, I'm going to go through the steps of how the tool works. So the whole technique, this thermoreflectance, the percentage of reflectance change due to temperature is usually very small. It's on the order of like less than 1% in this reflection change. So this technique for a steady state measurement is actually very noisy. So to reduce the noise, the way you can do this is by doing a lock-in averaging approach here. So this means that you are going to pulse your device, you're going to excite it at a certain frequency. So your device has to work repeatedly and be stable. So you can, for example, pulse it for 1 millisecond here. So we put that under the microscope, and then we shine our LED through the microscope, and that reflects off the surface. So then we have our CCD up here with all the different pixels, and that's open for a certain amount of time. So within that time when it's open, the LED is triggered at a certain frequency and at a certain duty cycle as well. Now the key here is that you're synchronizing the LED with the device excitation. So you're probing the temperature at a given time on the order of micro nanoseconds or even milliseconds. And you repeatedly do that so you can average that signal for a given delay. So after you average out for a given delay, you can measure the reflectance on an on state, but in between every time you measure in the on state, you could do one cycle in the off state. So you're measuring always a change in intensity of the reflection, and then you can estimate the temperature rise of those pixels there. So you can do that, and then if you want to look at another temperature rise at a different time delay, you change your time delay, and then you can build up this transient curve to get a temperature rise, and then look at the distribution of the temperature decay as well. So just to put into real pictures here, this is kind of what the setup looks like. The microscopes here, you have a CCD. You can't really see where we put the LED in, but in this case, we have a fiber optic, but we can also mount any other LEDs you have. Thor Labs sells them, and we can just mount them right there for any wavelength that we want. So this system here, you have these needles to go down and probe the device. You have this long working distance objective. And so you can power these devices at a certain frequency and then measure the thermoreflectance image here. Since these devices can go to high voltages or electrical capabilities, we have this very high precision tool for pulsed measurements where we can go up to 220 volts and we can pulse down to 200 nanoseconds a pulse width to the device. And we can measure the current, how it's changing across the device at the same time. Okay, so the key thing to measure the temperature rise, right, is that we need to get this coefficient. So this thermoreflectance coefficient that we call CTEH, the way it's measured is really that on this stage, two things that I guess I didn't mention about the setup is that there's a piezoelectric stage and a thermoelectric stage. So the thermoelectric stage can control temperature from 20 to 120 Celsius, and we do that for the calibration. So we keep it at 20 degrees, we measure reflectance, and then without biasing the device, we go up to 120 degrees and measure the reflectance. And you can also, you don't have to just go to 120, you can go to 180, and you can build up this curve here where you see the temperature rise versus the change in reflectance. And like I said here, right, you can see the percentage change in reflectance is just on the order of 0.02%. It's very small, but we can detect that, and you can see that it is linear in this case. On top of that, the piezoelectric stage, just to mention that there's an algorithm that's allowing it to autofocus to make sure you're always in the same plane of focus. As you can imagine, the reflection is going to change if you're not in the same plane of focus. So that's very key in order to getting reliable results that are repeatable. So here, what this is showing, okay, we can measure the metals very well, but can we actually measure the channel temperature where the hotspot is with the thermoreflectance technique? So as I mentioned, these are very high bandgap materials. The optics that we have are more catered towards the visible range. So most of these wavelengths that we use are going to transmit through the material as well. But you still get a reflection because the light's going to enter, hit the surface, transmit, and reflect off this bottom interface, and then there'll be some internal reflections as well. And I'm going to get a bit more into detail of that. But the main thing here was that by doing this, though, because it's transmitting through here, there was an underestimation of the temperature when you're measuring the thermoreflectance of the gallium nitride here. So one way to avoid this is to use a wavelength close to the energy of the semiconductor. In this case, 3.4 electron volts is how much the gallium nitride has as its bandgap. So a 365 nanometer LED would get you to that bandgap right there. Now, if you do that, you can see actually the reflectance changes. It becomes very strong, the relationship between temperature rise and delta R over R here. And you can use this coefficient to estimate the temperature rise. So one thing, however, before showing the results for that, the bandgap of the device here, though, is dependent on the residual stress. So these are thin film materials. When they're grown, the stress can change significantly on the way they're grown epitaxially. And it depends on your transition layers and what it's grown on. So while people, and the stress is also related to how many defects in the quality of the material is. So in a lot of cases, you can get here, this is just showing for gallium nitride, if it's strain free, this is what the bandgap would correlate to here. And for this device here that has a superlattice that reduces the stress here is pretty close to the strain-free value. The 365 nanometer LED is over here. So we're still lower energy. So it's not fully absorbing and being reflected, but it's also transmitting through the material as well here. And you can see the difference here when you have another device that has a different transition layer and the stress becomes more tensile in the device. That tensile stress results in shifting the bandgap, and now it's closer to 365 nanometers. And you can see there's an order of magnitude difference in this thermoreflectance change in this coefficient right here. It goes from -6 times 10 to the -4 to 10 to the -3. So this reducing the amount of interference from lower layers is going to improve your CTH and give you a more accurate result. Now, this is just the results of those devices there, and just showing you that when you're close to the bandgap, you can get a very accurate measurement. But when you're not close to the bandgap in that strain relief layer, when you're very far, the measurement of this channel temperature from this image here is much lower than the gate metal temperature. So we're using the gate metal here as a comparison of how hot it's actually getting. So the question here, though, is it still possible to use these signals to determine temperatures at lower interfaces, or is there even a way to backtrack from these sub-bandgap wavelengths the actual channel temperature? So another important factor on top of this as well, as the bandgap changes with the residual stress, uh, bandgap also changes with temperature. So this is one thing, if you're using a near bandgap measurement like this, you have to be very careful that when you get close to the bandgap and your bandgap's shifting because of the temperature, because the device is getting very hot, that your thermal reflectance coefficient is not becoming nonlinear. And there's if you look into this publication over here in 2020, you'll see that we looked at this effect, and you can see the nonlinear effects in the thermal reflectance coefficient when you get very close to the band gap here. Okay, so traditionally with this technique that I've introduced to you now, one way to measure temperature is to calibrate this, like we're saying, and then try to get a temperature rise. But there's really no verification of this measurement. Like you've calibrated a certain coefficient, and then you're estimating temperature rise. You could then go and do a second wavelength. Let's say that you have a reflectance, but then you get into this game of, okay, my coefficients, the temperatures I get from these two coefficients for different wavelengths are kind of close, but they're not that close. Which one's the one that's off? Do you know which one's further off? We don't really know. So you really need an alternative method for this technique to understand how good is your measurement using multiple wavelengths and which wavelengths are probably the outliers. And that's what I'm going to present today via hyperspectral approach here. So the hyperspectral approach here, to understand this a bit better about using different wavelengths, we also have to understand the reflectance of these thin film materials when you're below the bandgap, as I was saying. So first of all, just what's driving the change in reflection is the refractive index is changing with temperature here. So in the case when you're above the bandgap, your refractive index is changing linearly with temperature, and that's what's giving that good, nice linear relationship if you're at a single wavelength here. Now, when you're below the bandgap here, right, so the wavelength is greater than the bandgap, you don't only have the effect of the refractive index changing, but you also now have this spectra here, these peaks that are happening from this thin film interference effects shift with temperature. So the reason they're shifting with temperature is the fact that you have light coming onto the surface, going into the material, and then reflecting off these lower interfaces. And then what you're collecting with your CCD is kind of a contribution from all these reflectances from each interface, right? Now, if you think about these reflections from the lower interfaces, they're going to depend on how much they travel through the material and how thick is that material. When you're heating up the device, there's some thermal expansion happening in the device as well, right? So these layers are changing, and so that's shifting the wavelength of what you're measuring here. And so you can see that here, and this paper did a nice job of explaining this and showing that this shift in the wavelength is actually linear with temperature. And they show that if you're monitoring the shift in the wavelength, the temperature, you can get a very linear relationship. But sometimes now, if you're just looking at the intensity, how much is it changing, right, between the black and the red, which would be the change in the y-axis here, that's not always linear. And that's because, right, if this is shifting left and right, you could be finding yourself on one side of the curve compared to the other, and the coefficient could even switch signs in this case. So to understand, I guess, better these devices, these types of graphs need to be produced to understand which wavelengths to use when trying to do these thermal averages. Now, if you can get one of these spectras, then you can tell, okay, we have to be careful when we're towards the peaks or the troughs, but if we can measure the reflectance somewhere in between these slopes are pretty linear, and we can get a pretty good sensitivity if the slope is very steep, right? So if you can probe at different wavelengths here, here at like 540 nanometers, 610 in this specific device, you can measure the reflectance as we're saying, but we still don't know how we could verify the accuracy of this measurement. So what we did is that we got the spectra of our devices here. In this case, this is a GaN device on a diamond substrate. Diamond is used for enhancing the thermal dissipation. And we used different wavelengths and got the coefficients for all these different wavelengths here. So we specifically picked some that were above the bandgap or near the bandgap and some that were below the bandgap. Now, using this relationship that it should be linear, uh, the way we decided to verify the accuracy is plot now the change in reflectance versus this coefficient. And based on this relationship, if it should be linear, that line that you fit to this data, right, should be the temperature rise. So that's what we did. We plotted all these for different wavelengths. We applied our linear fit, and then you can get a goodness of the fit. And so if you see this, you can see that if there was any wavelength that was a bad measurement or something that was off in the coefficient or the reflectance change, it wouldn't go along this line, right? And we could remove any outliers here. So this is just showing this for like a small region of interest that is linear. Now what we can do with our software is that we could do this exact procedure for each pixel. And that means that you have to align all your images for thermal imaging with the calibrations to make sure that there's no discrepancies here. So this is kind of what it looks like. You have your image of your device here and with the channel and this gate metal. And then you can measure the reflectance change during operation. This is at 5.4 watts per millimeter. And then you can do your calibrations for all these different wavelengths here. And you can see how it varies quite a bit. So if you overlay these two and then you plot, you apply linear fit to each pixel, then you can get this hyperspectral map right here. So this is showing the hotspot in the channel right here next to the gate. And then what you can also produce, right, is the goodness of fit for each of these pixels. So producing the goodness of fit, right, is it now you have an indicator of how good this measurement is. If you don't have a good fit, your measurement of temperature in that area is not that accurate. And this can be seen here that your goodness of fit is very good for the channel, but this gate metal here, actually, this case is not that great. And that's actually, you can go back and look at this, but it has to do with the 365 nanometer image for the specific case, that you have a zero reflectance during operation, but in your calibration, you're having a non-zero effect here. So this is mainly the whole driver of this is that the calibrations is more like a steady state measurement. It's not pulsing. So you get a lot of noise involved in this measurement, and you can there's a high risk of getting a bad calibration here. So overall, this method, what it allows you to do is to use different wavelengths to verify the accuracy of your thermoreflectance image and see if you're getting the right temperatures. Okay, so now going back to that bias dependence point, we can now map the whole device and see what those simulations were generating based on different bias conditions. And we can see if that profile changes based on different bias conditions. So here is for 3 different gate voltages with the drain voltage changing to match the power density. And you can see here that the peak temperature in this particular device is actually not shifting that much, but the peak temperature is changing a bit while changing the gate voltage here. The reason the temperature is not shifting that much is that we have a very large channel in this case. You can see it's from 6 to like 15 microns here. So we're allowing a lot of area for this device to spread out heat. But in an RF device, this channel spacing is only like 6 to 8 micrometers or even less. You want to get down to like 1 micrometer. So looking at these images, you can see how this going to more negative gate voltage, you're localizing this heat and you can estimate that temperature of the device. Okay, so apart from doing this just with thermoreflectance, we also wanted to just verify these temperatures with another technique. So we had structures that have these gate resistant structures where you can monitor the resistance of the metal, and we compared these two, and we got very similar temperatures here. So that made us feel a bit better about these results. So on top of the thermoreflectance and doing these types of measurements, the second technique I wanted to talk about today is actually about scanning thermal microscopy here. So this is a contact technique using an AFM. This is primarily work that was done at the National Institute of Standards and Technology, but we're also bringing the capability here. So here you take this fine thermocouple in the size of 50 nanometers, and you can put on the surface and scan across the surface. This is kind of what the setup looks like. You put your chip down in a package, you put wires down, and then you can power the device. Now, when you scan with an AFM with this, you still have the laser on top, so you can get a height profile map here. And you can see this is the same device that I showed you with thermoreflectance, where we could scan across and get where the metal is, the gate metal, and then see the channel as well here. So in this case, we scan across an area of half the device. Actually, it's very similar to the image that we showed you, just half of that image. And we can measure the temperature here. So the process is that it's a thermocouple, it's measuring a voltage. You calibrate that to some type of microheater. Um, and you can get a linear relationship between the voltage and temperature, and then you use that to estimate the temperature based on the thermocouple voltage. Now, doing this for the different bias conditions for a very specific area here, you can see the heating and how it changes here. So this color map here right now is just in voltages for different power dissipations. But in the next slide here, which you can see is that we converted this with our coefficient here, and you can see the change in temperature of the channel there and how it increases. So from here again, going from a 0 to negative voltage, you're basically pushing down your electrons in the channel and creating this depletion region. And then these electrons are causing more heat to generate, and then you get this higher temperature profile here. The main thing here is really we have these capabilities. For this device, it's large. It doesn't show the advantage of this technique, but we can measure down to a resolution of 150 nanometers. If you're trying to see some temperature localized hotspots on that order, it's possible to do with this technique. Now, the last case that I wanted to show, I think I have 5 minutes before we stop here, but I'm almost done. It's only 4 slides here. Is that I talked about gallium nitride as a great material, but now people are looking into the next materials that have even higher band gaps. So there's been a very big push to look at materials such as gallium oxide and also high aluminum content, aluminum gallium nitride. Now these materials, their band gaps, just to give you an idea, they go from this 3.4 electron volts, you can get up to like 4.9, and in some cases, aluminum nitride, you can get up to 6 electron volts. So there's promise here to make your devices even smaller, but now you've run into a problem based on the structure of these materials that once you start having oxides, right, you reduce the thermal conductivity of these materials significantly. The dream would be to get to diamond where you have a high thermal conductivity, but it's pretty hard to make devices right now with diamond. So now we have a thermal problem of inherent low thermal conductivity. We want to know the temperature, and now we have to think of other approaches to reduce the temperature in these devices, and maybe sometimes active cooling techniques here. So the only thing though is, I just wanted to wrap this up here, is the thermoreflectance. Now this whole technique of, we can either do sub-bandgap thermoreflectance when it's a heterogeneous interface between the substrate and the semiconductor, but if you have a homogeneous case where the substrate is the same material as your thin films, this thin film interference effect becomes a lot less pronounced. So trying to do your near bandgap measurement now, you need to go to way smaller wavelengths and shorter wavelengths. Now that changes the whole optics of the system. And one of my students has been developing this microscope where we're going to try to do these DUV thermoreflectance measurements to get the temperature of these types of devices. There's also another phenomena that we've discovered looking at these devices for thermoreflectance, not near the bandgap, but sub-bandgap. And this is the case for gallium oxide here, where if you see the spectrum of reflectance versus wavelength, you see there's a very high reflectance in this 470 nanometer range. Now the bandgap is like around like 260 nanometers. Now, if you look at this, it's from a previous paper a few years ago. People did photoluminescence of these gallium oxide samples, and they see that there's a defect around this area. So it looks like when you get a defect, you can cause absorption at a given wavelength if you hit the energy level of that defect, but you can also get this reflected signal that you could use for temperature. And we went ahead and looked at this, and this is a paper that's published. Sorry, the reference isn't there, but we verified the temperature of the channel using this 470 nanometer wavelength, and we compared it to scanning thermal microscopy, and we got very good agreement as well. So overall, I just want to conclude by saying that hyperspectral thermoreflectance is providing you a quantitative assessment of the TTI's accuracy through the goodness of the fit. This allows you to use sub-bandgap wavelengths to avoid carrier excitation in the device as well. So that's one thing I didn't talk about, but your device, you have electrons flowing through there. If you're putting in photons that have the same energy, you could actually excite more electrons into the channel and alter the device physics. So trying to get the sub-band gap measurement is a very uh, good idea to avoid this happening. And then in terms of future work, what you want to do is take all these different heating profiles for different bias conditions, average them, and then predict what your temperature profile would be under very high frequencies under the gigahertz. So yeah, so I'd like then there to leave some time for questions. I'd like to acknowledge my advisors, which a lot of this work started from, Sam Graham from a PhD and Andres Antrone at NIST. And then also some collaborators who provided the devices here from the Naval Research Lab and previous students as well that were in my lab. So thank you.
Thank you so much, George, for the insightful and very clear presentation. Very interesting. Okay, so now I will open the floor for questions. So if you would like to ask a question, please feel free to raise your hand virtually here on Zoom, or you can type your question into the chat and I will share it with our speaker. Okay, so okay. Well, in the meantime, I have some curiosities. Regarding the thermoreflectance imaging, I would like to know, just for curiosity, which is the resolution? So, which is the minimum temperature that this technique is able to detect?
Minimum temperature rise. So I mean, it depends how good your coefficient is, but I would say for that range of 10 to the -4, almost going to 10 to the -3 coefficients, the minimum I would say is around like 1.5 degrees temperature rise is the minimum.
Okay. And I was also curious about uncertainty evaluation, because I think it is quite difficult to get an indication about how good the measurements are performed. So I was just curious about how you perform the uncertainty analysis, which parameters you considered for that.
Yeah. So what we normally do, yeah, because there is a large variation. I'm going to show this. So since the temperature that you're measuring is a function of the calibration coefficient and plus the reflectance change that you're measuring, what we would do first is we do a propagation of uncertainty where you take the goodness of the fit of your slope here, of your uncertainty in your calibration. Then you would incorporate that into your temperature measurement by also then for a certain region where you're measuring temperature. So instead of just taking here, sorry, let me show like a picture of a device here. So for example, this area here that we have like the green ROI. So we would average the reflectance change for all the pixels in that area, get the standard deviation, and then try to find the uncertainty for that region. So then you could get the standard error of that area, and then you could incorporate the error from the coefficient from your calibration experiment. And then that's how we can calculate the uncertainty and the temperature for that area.
Okay. Okay.
And then the goodness of the fit for this hyperspectral probe, the whole purpose is to see, is your calibration coefficients actually good? Because if something's off, you would see it in this graph here, that it wouldn't be along this line.
Yeah, there it deviates. Okay.
Yeah.
Okay. I have actually another question. I was just curious, maybe I missed some information in slide 27. You talked about, yeah, the translation to imaging. I was just curious to better understand about these, the conversion, the pixel alignment, and yeah, just to understand about the, let's say, the evaluation procedure that you followed, starting from the images.
Yeah, so I guess first of all, for the actual image, to make sure it's actually taking the image at the same location every time, the piezoelectric stage is what's keeping it in the exact same position. So because since we're taking an image like that image on the left here, the CCD, you can create an area of focus, and then your piezoelectric stage is going to keep on moving the stage to make sure you're always in the same area of focus. So you need features to get the auto-focusing function. Then post-analysis for what's happening here is, well, it's also based on these CCD images. If your image is slightly moved compared to your calibrations, they have to be aligned up. So our software, this is actually a commercial software that we're using with the company. They're called Microsange. Uh, they have a procedure where they can align those images together based on your CCD images, and then they're ensuring that you're taking the pixels for your reflectance measurement the same area as the calibration. So that's what's happening there in terms of the alignments.
Yeah, okay, it's clear. Okay. And okay, there's a question. Oh, there are two questions actually. So maybe we can start with Arthur Oliveira, if you want. Thank you.
Hi, George. Thank you for your presentation. Very nice. Actually, I'm sorry if I missed something because for a moment I still had to call you and I maybe missed for a brief second. But
No worries.
that reminds me, for example, can you show the equation again in page 26, I guess?
Yeah.
Actually, just to be sure, you said that's a linear relationship, right, between the reflectance change with the temperature. So in this case, do you take a reference point and then you always use a linear law for the temperature measurement, or do you take temperature increments that are always like, let's say, incrementing from previous measurements? I don't know if I was clear.
I think I know what you're at. So like, yeah, so first of all, yeah, the linear relationship, we have to be careful to make sure it's in the region that's linear for the certain temperature range.
Yeah.
But what's happening, so this device, we're inputting the same power into the device for every pulse when we're averaging. So we're assuming, because if it's the same power, it should be the same temperature rise every image we're averaging. But for the calibration, we do different temperature increments to get the reflectance at different temperatures to find out that it's linear. But the image itself, so yeah, it's not just we measure one time cold and one time hot. It's like we're measuring cold repeatedly because there could be heat accumulation effects.
Yes.
So this is a pure temperature rise. It's not an absolute temperature. It's like whatever dynamic equilibrium you hit, you're measuring temperature rise.
Okay, thank you.
Yeah.
Okay, I see Matthew. Matthew, if you want to ask your question.
Yeah, thanks so much for this is interesting. So yeah, our group does a lot of infrared thermometry stuff. So it's nice to see some of the other advantages of this technique. I was just kind of curious about the mechanics of the measurement, specifically the plot you had. You had this nice plot showing the entire temperature profile of the throughout each element, like throughout each layer of the substrate. I think it was the reflectance technique. I think you had it for both, but that was the one that caught my attention.
Which one?
I think it was a bit before the maybe a bit before no. It was right before you transitioned to that second technique.
Oh. Okay. This or
Yes, I think it was maybe this one. Yeah.
okay.
Yeah, it was this one. I was just curious, like to actually make this measurement where you see the temperature rise over the entire distance, like what do you have to do repeated measurements to reconstruct this temperature distribution? What's the like time duration to evaluate this measurement profile? Do you do like a steady gate voltage and then reconstruct this temperature profile? That's what I was curious of.
Oh yeah. So this as it's at a given time delay. So this is at the end of the pulse, so it should be the peak heating. But the image itself, so this is a hyperspectral image. So this is composed of multiple images at different wavelengths. But let's say, just to give you a sense of the time, if for one image, so you're acquiring basically the change of reflectance for all the pixels at the same time. So you're generating this image for one wavelength and one time delay, constant time delay.
Right.
We could average this over, I would say maybe like 2 minutes, 2.5 minutes to get one image. And then if you want to do this for like 5 wavelengths, is it like 10 minutes? And then the rest is just post-processing for that part. But this is pulsing. It's 2 minutes, but you have to think about like these pulses are on the order of like 100 microseconds, 400 microseconds. So you're averaging over a lot of cycles here.
Right. So in theory, one image is a very short period of time, and you're just averaging it a few different times just to, yeah. And then you have to go across different wavelengths to then get the entire field, is that, or get the entire profile across this material. Is that right?
Yeah, correct. So you don't have to do all the wavelengths. That's just if you want to do this hyperspectral approach. If you
Okay.
like, for example, metals, if you just wanted it, you could trust the reflectance off a metal pretty well. You could just take one image at one wavelength. But then if you want to look at the transient temperature rise and decay, then you have to multiply that images by all the time steps you want to take.
Right.
So yeah, you could spend like if you want to get a full transient temperature rise and decay, it could take around like 30, 40 minutes.
Okay. Okay. And then just a follow-up, because I think the measurements you said are mainly temperature rises with respect to something. Is that correct? They're relative temperatures compared. Is that true?
Their relative temperature. So yeah, I did want to present other work on that topic, but we haven't published it yet, so I'm just being careful there. But
Yeah, of
there
course.
is so there is the gate resistance technique. Since it's an absolute temperature measurement, we've been looking at the correlation between these temperature rises and the absolute temperature because there are heat accumulation effects, especially when you have a bad thermal conducting substrate. But there is a way to relate these two. If you have like the steady state thermal resistance, and then looking at these transients, you could relate it based on the duty cycle that you have, that you're pulsing these devices at.
Yeah, okay.
So you could find out the peak temperature from that.
I see. Okay. Got it. Those are my questions. Thank you.
Yeah, great questions.
Okay, I don't know if there are any other questions. We still have, let's say, 4 or 5 minutes. Let's see from the audience. No other questions. Okay, I think that we can stop here the session. So I would like to thank George again for your very interesting and insightful presentation. And I also want to thank Matthew for organizing this interesting session. And I want to thank all the audience for attending this session. So thank you to everyone and enjoy the rest of the day. And see you on the next session of TTC.